In this lecture, we're going to talk about the derivatives and integrals of vector functions. So it turns out that these three very important things in calculus, limits and derivatives and integrals. So if I want to take a limit or a derivative or an integral of a vector function, well, they all act what we call component-wise. And all that means is that you just take the limit or derivative or integral of each component of your function separately. So for example, if r of t is given by, say, f of t, g of t, this two-dimensional vector function, well then r prime of t is just f prime of t, g prime of t. So it works in kind of the most straightforward way that you could have hoped for. And what I want to talk about more in this lecture is what the derivative of a vector function really kind of tells you. And to do that, it'll be helpful to draw a nice picture. So we're going to look at this in the context where r of t is the position vector of an object. So say you have an object that's moving in the plane. So if I pick some point in time and plug that t value into r, then I get a vector that points from r to wherever that object is at that point in time. So say this one right here is r of t. And then maybe a little bit later, if I plug in a slightly larger t value, maybe t plus delta t, well then I get the position vector that points from the origin to its new position. Now from those two vectors, I can take their difference, and I get a new vector right here, which is the difference between r of t plus delta t minus r of t. But now the way we define r prime of t, I mean, it works component-wise, like I said up here, but you can also think about it as being the limit as delta t goes to 0 of r of t plus delta t minus r of t, and then all divided by delta t. That's just the limit definition of a derivative that we've seen a whole lot. So what's going to happen is that you're going to basically take these 2 points on this curve and kind of bring them closer and closer together. And then you end up with a vector that has a certain direction, and that direction is going to end up being tangent to the curve. So in the limit, when you look at the derivative of r at this point, say, then you're going to get a vector that looks something like this. So this is a tangent vector. And in fact, in the case where r is the position, then r prime is going to be your velocity vector. So your velocity is, of course, changing over time as you move along this path. And your velocity is always tangent to your path. Now we're going to make another definition that's sometimes kind of useful. We define the unit tangent vector capital T of t. Well, it's just the unit vector of r prime of t. So you take r prime of t and you divide by its own magnitude. Of course, here I have to assume that r prime is not the 0 vector. Okay, now we can take a problem like what we did in Calculus 1. So in Calculus 1, you find the tangent line to a function graph at a point. And now let me show you how we can find a tangent line to a parametric curve, in fact, even a three-dimensional one. So let's say that r of t is defined by t squared, t cubed. And let's find the equation of the line that is tangent to r of t at the point -2, 4, -8. Well, remember that in order to write the equation of a line, we need two ingredients. We need a point, which we already have, and we need a direction vector. And so the idea here is that the direction vector is going to be r prime of something, right? Not just r prime of t, but r prime of a particular t value. And I'll come back to that part in a minute. Let's just find r prime. So we take the derivative of each of the components separately, and so we get 1, 2t, and 3t squared. So now what do I plug in? Well, the idea is that the point that I was given, -2, 4, 8, that is r at some t value. And in this case, it's pretty clear because the first component of r is t, so this must be just r of -2. And so I'm going to take that same t value and plug it in over here. So r prime of -2 is the vector 1, -4, 12. So there's your direction. Okay, now let's just write the parametric equations of that line. So x equals y equals z equals, we put the point here in the first column, and then the coefficients of t come from the direction vector. So 1t, -4t, and 12t. Or if you wanted to, you could also write this as a new parametric equation. We shouldn't call it r of t anymore. I don't know, how about maybe L of t? And so you could call that -2 plus t, comma, 4 minus 4t, and then -8 plus 12t. Okay, so either of these forms, either in parametric form or in vector form. Okay, next time we'll dig in a little bit deeper into velocities and accelerations of objects moving in the plane or in space.